Netflix spends over $13 billion annually on content, yet 80% of shows discovered are through recommendations. What if those recommendations were irrelevant? Today, we'll design a recommendation system that handles billions of daily interactions, ensuring users find content they love, driving engagement and retention. Here's what most engineers get wrong. They underestimate the complexity of scaling personalized recommendations. Remember those 13 billion items? We'll see why that matters when we get to sharding. The secret is understanding the interplay between candidate generation and ranking. First, let's define the scope. Functionally, we need to recommend relevant items to users, personalize recommendations based on user history, and support real-time recommendations. Non-functional requirements include low latency, under 100 milliseconds, high throughput, millions of requests per second, and high availability. A key clarifying question: do we need to support explicit feedback, ratings, or implicit feedback, clicks, views? Let's assume implicit feedback for this design. We'll use this implicit feedback later when we discuss A/B testing strategies. We also need to consider diversity and fairness in our recommendations, ensuring users aren't stuck in a filter bubble or unfairly targeted. This is crucial for long-term user engagement. We need to handle millions of users and billions of items, which introduces significant scalability challenges. Let's estimate our scale. Assume 100 million daily active users, DAO. If each user generates 10 recommendation requests per day, that's 1 billion requests per day, or roughly 11,500 requests per second, QPS. For storage, if we store 1 kilobyte of data per user for recommendations, that's 100 gigabytes of data. Considering a 3-year history, that's 100 gigabytes times 3 times 365 equals 110 exabytes. Bandwidth, assuming 10 kilobyte response size per request, that's 11,500 rec per second times 10 kilobytes equals 115 megabytes per second. But here's the twist. We also need to store item metadata. With 13 billion items, storing even 100 bytes per item adds another 1.3 terabytes. This is where most people go wrong. They forget to account for growth and future feature additions, so always pad your estimates. We also need to consider the storage for pre-computed features, which can easily double our storage requirements. This estimation is crucial for choosing the right technologies and scaling strategies.
Now, let's look at the high-level design. Our high-level design separates read and write paths for optimization. The write path handles user interactions and model updates, while the read path serves recommendations. For the write path, user interactions hit a load balancer, then the API gateway, and finally the app servers. Data is written synchronously to a primary DB and asynchronously to an analytics DB via Kafka. The read path involves the same initial steps, but the API gateway first checks the cache. On a cache hit, the recommendation is returned immediately. On a miss, the read replica is queried and the cache is populated. We use a CDN to serve static content and a rate limiter to prevent abuse. We use Kafka because it provides ordering guarantees and fault tolerance, unlike a simple queue like RabbitMQ, which can lose messages. Your interviewer will push back here. Why not use a message queue with exactly one semantics? The answer is that exactly one semantics often come with a performance penalty, and Kafka's at least one semantics combined with item potency in the consumers is sufficient for our use case. Stop. Think about this. Why separate read and write paths? It allows us to scale each independently based on their specific needs. We'll use the API endpoint post-API v1 recommendations with user ID, item ID, interaction type for recording user interactions. The trade-off here is increased complexity in managing two separate paths.
Now, let's dive into the core logic. The recommendation process has two stages: candidate generation and ranking. Candidate generation retrieves a set of potentially relevant items. Common techniques include collaborative filtering, user-based or item-based, content-based filtering, and popularity-based recommendations. We'll use a hybrid approach, combining collaborative filtering and content-based filtering, because it leverages the strengths of both. Collaborative filtering identifies users with similar tastes, while content-based filtering recommends items similar to those a user has interacted with. For ranking, we use a gradient boosting model, like XGBoost, to predict the probability of a user interacting with an item. Features include user history, item attributes, and context. To balance exploration and exploitation, we use an Epsilon-Greedy strategy, where we randomly recommend a new item with probability epsilon. A common mistake is focusing solely on accuracy. We must also consider diversity. Your interviewer might ask, why not just use deep learning for ranking? Deep learning models can be powerful, but they require significantly more data and computational resources. Gradient boosting offers a good balance of accuracy and efficiency for our scale. We can use techniques like FAISS for approximate nearest neighbors to speed up candidate generation. FAISS creates indices that allow for fast similarity searches using the HNSW algorithm. FAISS is used because it allows for efficient similarity searches in high-dimensional spaces, but the trade-off is increased memory usage. A potential failure scenario is a sudden surge in new items, which can degrade the performance of the ranking model. We can mitigate this by regularly retraining the model with the latest data. The Epsilon-Greedy algorithm helps us explore new items, but it might recommend irrelevant items to some users. We use collaborative filtering because it leverages user behavior to find similar items, but it suffers from the cold start problem for new users. The algorithm we use is XGBoost, a gradient boosting algorithm that excels at handling structured data and provides feature importance, but it can be computationally expensive to train. We use XGBoost because it can handle nonlinear relationships and missing data, unlike linear regression, which assumes linearity and requires imputation.
Let's design the data model. We'll use PostgreSQL for the primary database because it offers strong consistency and ACID properties, ensuring data integrity. Key tables include users, items, and interactions. The users table stores user information, user ID, sign-up date. The items table stores item metadata, item ID, title, description. The interactions table tracks user item interactions, user ID, item ID, interaction type, timestamp. We'll add audit fields like created at and updated at to each table. For feature engineering, we'll store pre-computed features in a separate table, user features and item features. Pause and think. What's missing? Data lineage. We need to track the source of each feature, so we add a feature source field to the feature tables. We'll also need indexes on user ID and item ID in the interactions table to speed up queries. Feature engineering is crucial for improving the accuracy of our ranking models.
To handle our estimated 11.5K QPS, we'll use caching, replication, and sharding. We use Redis as a cache-aside cache to store pre-computed recommendations because it provides low latency access, typically under 5 milliseconds. A high cache hit ratio, 90% plus, is crucial. We replicate the database using leader-follower replication for read scalability. For sharding, we'll shard the users table based on user ID. Remember those 13 billion items we mentioned in the hook? Sharding allows us to distribute the metadata for those items across multiple database servers. We use a CDN to cache static content like item images. To analyze bottlenecks, we'll monitor key metrics like QPS, latency, and error rates. What happens if the database goes down? We'll need a failover mechanism to switch to a replica. This is where the 100 millisecond latency requirement becomes challenging. We could also use consistent hashing for sharding, but the downside is increased complexity in managing the hash ring. An experienced interviewer will probe what happens at 10x scale. Here's the key. We'd need to reshard our data, potentially using a more sophisticated sharding strategy like consistent hashing with virtual nodes to minimize data movement. The downside with caching is that we need to handle cache invalidation, which can be complex. We use sharding because it allows us to horizontally scale our database, but it introduces complexity in data management and querying. We use a CDN because it reduces latency for users by serving content from geographically closer servers, but the trade-off is the cost of CDN usage and the need to manage cache invalidation across the CDN.
Now, let's consider reliability. For fault tolerance, we'll use redundancy and automated failover. We'll have multiple replicas of each service and database. We'll use a monitoring system, like Prometheus, to track the health of each component. We'll set up alerts, using Alert Manager, to notify us of any issues. To evaluate the system, we'll use A/B testing to compare different recommendation algorithms. We'll also use online and offline evaluation metrics. Online metrics include click-through rate, CTR, and conversion rate. Offline metrics include NDGC and MAP. We use A/B testing because it allows us to measure the impact of changes in a real-world setting. For example, we can compare a new ranking model against the existing one by splitting traffic 50-50 and measuring the change in CTR. The downside here is the cost and complexity of setting up and managing A/B tests. Another downside is that A/B tests can sometimes be misleading if not designed carefully. We use Prometheus because it's a powerful monitoring system that can collect metrics from various sources, but it requires careful configuration and management. We use Alert Manager because it allows us to define complex alerting rules and route alerts to the appropriate channels, but the downside is the complexity of configuring and maintaining the alerting rules.
In summary, we designed a scalable and reliable recommendation system using candidate generation, ranking models, caching, replication, and sharding. A key consideration is the balance between accuracy and diversity. Future steps include addressing the cold start problem by using popularity-based recommendations for new users and ensuring fairness by mitigating bias in the training data. We also need a rate limiter, cache/Redis, and a rules engine to handle edge cases and business logic. This rules engine could be implemented using Drools, a business rules management system, allowing us to easily update rules without redeploying code. The consideration between accuracy and diversity is that focusing solely on accuracy can lead to filter bubbles, while prioritizing diversity can reduce the relevance of recommendations.
Want to master more engineering concepts and coding patterns? Subscribe for weekly tutorials that answer the questions developers face in real interviews and projects.